In this video, we'll understand about charging a capacitor through this resistor R. We have a battery of voltage, a DC battery of voltage E, and then we connect this battery. Let us assume that there is a switch here, and at time t equal to 0, we connect the switch. The current starts flowing through this resistor and starts charging this capacitor. There are few things you need to mind. This voltage E eventually charges this capacitor to a charge Q, and that Q is given by C into voltage V. What does that mean? Let's say if this is a capacitor of capacity 1 farad, let's say, and this is a voltage battery of 10 volt, then the final charge on this will be Q is equal to 1 farad multiplied by 10 volt is equal to 10 coulomb. The problem is this 10 coulomb does not charge instantaneously. That flow is not instantaneous. Why? Because we have a resistor here. Let's say this resistor has a value of 1 ohm. Then, assuming if this where we had short circuited it, there will be a current flow, and that current will be I is equal to V divided by R, or a 10 ampere of current. So the 10 ampere of the current will have to charge for 1 second, only then it will take 10 coulomb of charge will charge. So the whole thing is going to take 1 second. If we increase this resistance to, let's say, 10 ohm, then the current will reduce to 1 ampere, and the 1 ampere of the current will have to charge for 10 seconds to get a charge of 10 coulomb. As we increase the resistance, the charging of, so the whole charging process takes time. It's not an instantaneous process, because instantaneously charge it will require infinite amount of current in a very instantaneous amount of time, which is not possible. So how does the charge on this capacitor varies? How does the voltage on this capacitor vary? That's the equation we are going to derive, which will make use of the calculus. We'll have to use the integral calculus, and make sure you watch this video all the way throughout this length, because we will have a very interesting practical circuit that will show how it's charging. To give you an idea, I have drawn up a circuit like this, and I will show a charging and discharging of this capacitor. But before that, we'll go into the theory of this circuit, and this is what the equation looks like. We'll simply written the electric circuit equation. The voltage E of this battery is equal to the current through this resistor, the voltage across this resistor, which is I into R, plus the charge on the capacitor is given by V is equal to Q by T. We have written bracket 3 here, which means that the current on this resistor is varying with time. R does not vary with time, the C does not vary with time, and E does not vary with time. So we have explicitly written T because the current through the resistor is varying with time. The charge that is accumulating on this capacitor is a function of time, it's varying with time. Usually we could also omit this if we could write I in smaller and Q smaller, but for now, just to make sure you understand that Q is a function of time and I is a function of time, I have explicitly mentioned T here. Now this I can also be written as is nothing but the rate of the change of the charge. If you just monitor the charge keep accumulating on this capacitor and then count the charge, then find this, it's a rate of change in a unit second, that is Q dQ by dt. We rearrange this equation. We need to solve this whole equation for Q. So what we do is we separate this q, the differential terms on one place and q on other side. So r into dq by dt is q by c minus e, and this is nothing but e into c minus qt. E into c minus qt divided by c. Just a rearrangement of these terms. We can do ce minus q, it goes on below here, it becomes dq divided by ce minus qt is equal to r, we take it here, and that becomes cc cancels. So this becomes rc into dt goes over here. So we can write dq into, if we integrate this whole term, we get this terms in terms of q and this term in terms of t. So we have dq by c minus q2 is integral rc. Now the charge is varying from q to any current value q, which is called q is equal to q, and this time varies from t is equal to 0 to t is equal to t. If we integrate it, it becomes minus log ce minus qt with minus, because we have a minus term here, so this thing becomes minus here. It's actually divided by minus 1, so minus terms comes here. Q equal to 0 to q equal to 1, that becomes equal to t divided by rc. And when we do this, we get this term. When q is equal to q, it's log ce minus q, and when q is equal to 0, this becomes log ce. Now log a minus log b is log a by b, so we have log ce minus v, log ce minus q divided by log ce, minus terms comes here, becomes minus t by rc. This should be plus here, so this minus terms comes, this should be plus here, so this minus terms comes here, becomes minus t by rc. This logarithm is the natural scales, so we have e to the power minus t by rc is equal to ce minus q divided by ce. If we rearrange the term, we eventually get q is equal to ce 1 minus e to the power minus t by rc. C divided by c is 1 minus q by c is equal to e to the power minus t by rc. So if we take e, this whole term here is 1 minus e to the power minus t by rc, and this term here, so q by c, and then c is multiplied, we get this term. What does it say is that the q is varying with t in this fashion. If you want to find the voltage on this capacitor, this is given by q by c, and q we know is a function of t, and then when we say the voltage on the capacitor, it's probably better to write it as a small v, and maybe write it as a function of t is equal to q by c is equal to e multiplied by 1 minus e to the power t by rc. And this is a plot of v with respect to the time. Now as t goes to infinity, v is equal to, we can write it as 1 minus 1 upon e to the power t by rc. If t is infinity, this term becomes infinity, and 1 by infinite is equal to 0. So v becomes equal to e. And that's what it says. Eventually, the charge on this capacitor becomes equal to the charge of the battery. But it does not happen instantaneously. It grows fast initially and then slows down when it starts saturating the voltage. And when t is equal to 0, then the voltage, this term, we have when t is equal to 0, it's e to the power 0, 1 minus, and e to the power 0 is 1, so 1 minus 1 is 0, v is equal to 0. And that's what it is right here. Initially the charge on the capacitor is 0, eventually it becomes e, and somewhere at the time t is equal to rc has a special case, which and this value of time has a special name, and it's called the time constant. and it's because it's mathematically becomes equal to calculate when t is equal to RC, this term becomes e to the power minus RC by RC, or e to the power minus 1. At that point of time, the voltage V will be equal to E multiplied by 1 minus 1 upon E. Something like this we have shown here. T equal to RC, voltage is equal to e to the power of minus e to the power minus 1. We now you can actually take any values, other value, for example RC by 2, 2RC, and so on and so forth, and plot this curve. Now we'll turn into this to show that we have this formula followed in a real experiment, and that's where we bring in this circuit, this actual circuit. I've tried to make this arrangement so that you can reproduce this experiment at your home with very inexpensive things. This is a 9-volt battery here, very inexpensive to find, but you can also use any simple 3-volt to even 1.5-volt battery. This is one I've chosen because I had this battery and it's easier to connect the wire on these terminals. With a regular 1.5 volt, it gets a little harder to stick the wires into it. This is a switch, simple switch. We can turn it on and off. You don't need this. You can just connect it and then touch the wire, and that will also act as a switch. But because I have to record the video, it's better I use this switch. The next thing here, I have a 220 microfarad capacitor. I will try to show you by bringing it closer. If you read it, it's something like 220. That's what it says, 220 here. And then I have a resistor here of value 100K. And you would not like to know why I chose these particular values, 100K and 220 microfarad. And the reason has to do with the fact that the time constant, if you calculate the time constant, 100K into 220 microfarad becomes 100 into 10 to the power of 3 multiplied by 220 into 10 to the power minus 6, and that effectively becomes, if you do like this, 100 into 10 to the power 3 multiplied by 200, 220 into 10 to the power minus 6. This becomes 10 to the power minus 3, and which takes away these 3, it is 22 seconds. Which means that somewhere around the middle of the charging circuit, it will take 22 seconds, which is how we can observe the voltage across this capacitor to do that. So to start the experiment, we will make use of this multimeter, and in this multimeter we can turn it on to the voltage reading, which will measure the voltage across the capacitor. And I have these two leads of this capacitor. One lead I am going to put somewhere on this negative end of this capacitor. But before we do that, let's measure the voltage on this battery, which you can see here is 9.37 or 9.38. I'll take it 9.37. It's a more rational. The switch is right now off, and now I connect this negative voltage, the negative end of this capacitor. I may have to restart this experiment if it fails somewhere, but maybe because the wires are like hanging around, and then so I have a paper where I record the voltage at different point of time. This is how I'm going to record my voltage here on this paper as the time goes by. So, and also I'm going to use a stopwatch to. I have another cell phone in which I'm going to record the time. So this is my stopwatch, and once I start my experiment, or I also start my timer, and then I am finally touching this thing on the positive of this capacitor, positive end of my capacitor. I am not almost ready for my experiment, and I am going to turn the switch to on and also start my stopwatch and start recording the voltage here. So as I turn it on, you see that the voltage is increased. I have my stopwatch running and I have recorded V equal to 0. At 5 we have 2.66. At 10 we have 3.69. At 15 we have 4.8. At 20 we have 5.4. At 25 we have 6.05. You see it's slowing down, the voltage increase is slowing down. At 30 we have 6.6. At 35 we have 6.9. It's not very accurate, but I am hoping we should just for 40 we have 7.2. At 45 we have 7.47. At 50 we have 7.65. And 55 we have 7.80, and I'm going to stop it here. But you see that the voltage increase has slowed down. It's now the voltage across this capacitor is slowing much slow, is growing much slower than it was initially. And if you observe, we have this voltage on this battery was 9.37, and if you leave it for a very long time, it's going to eventually reach to 9.37, and this is what I have recorded on my paper. It's not obviously going to be very accurate because I could not grab this my time very fast. When I tried to capture my time, I was off by like 1 second or something, but it should be pretty close. The general shape of the curve should match with whatever reading I had, and you can see that initially the voltage in the first 5 seconds it grew rapidly from 1 to something like 2.66, and then it grew in the next 5 seconds, it grew only 1 second. So the general trend of the curve is matching with what our expectation was, and you can see that this voltage has now started on this capacitor has started growing naturally. So I would like you to grab a battery, some simple resistor you can find on Amazon or Flipkart or anywhere, and then use a capacitor. If you try to get a bigger capacitor and try to choose a capacitor and resistor value so that the time constant is in real time, and then you can use a simple voltmeter or a multimeter. It comes like $20 or something, and then you can reproduce this whole experiment. What we will do now is go back on an Excel sheet, put everything on an Excel sheet, and we'll calculate and measure how the things look like. In this Excel sheet, I have tried to put everything. The voltage value is 9.37. We have a 100k resistor and a 220 microfarad capacitor, and I'm trying to calculate the value of the voltage at t equal to 5 seconds, 10 seconds, 15 seconds, and so on and so forth. This formula says that the voltage at time t equal to 5 seconds is equal to this voltage $d$3 is the fixed voltage 9.37 multiplied by 1 minus e to the power of minus T, which is C7 here, divided by RC, which is D multiplication of these two, and then I have multiplied by 0.001 because 10 to the power 3 multiplied by microfarad is 10 to the power minus 3 is 0.001. So if I give this, the voltage at t equal to 5 seconds should be 1.90, and at 10 seconds 3.42, 4.60, and so on and so forth. In our experiment, we observed my reading says here 2.6 volt, and the reason I can recall is that I started the stopwatch. There was mismatch in the time when I started this stopwatch and when I turned the switch on, and that's why what while this has to be at 5 seconds, I possibly observed this voltage at 2.66 volt. And also because the capacitor value, which it shows 220 microfarad, in reality this could be a little lower or more than, because the capacitor has a tolerance of 20%, so it can be off by 20%. But if you observe the pattern, it's 3.42 here, and I observe 3.69, 4.60 here, I observe 4.8, 5.59, I have 5.4, 6.36, I have 6.05. It's matching pretty much closely within the range of the errors in actually observing it. If I had a better experiment, I could have done, for example, an oscilloscope. If I could use an oscilloscope, it would show more precisely the curve of a charging of a capacitor. But nonetheless, this provides a very low cost verification of some of the theories that you can reproduce at your home. I encourage you to do these things.